Hello and Namaste. I'm Shailendra Shastri and I welcome you to my YouTube channel. In this video, I will demonstrate how to make use of Smith chart. But before that, I will take you to the known world of impedance plotting technique on ordinary graph paper, and then later on, the same technique will be extended to understand the construction of Smith chart. Before we jump onto the Smith chart for the designing of high frequency circuit, it is always better to have a little background how to plot the impedance on ordinary graph paper. And the same concept can be further extended to understand how to plot impedance on the Smith chart, and later on that concept can be used to understand how to design RF circuitry using Smith chart. So for that, we'll start with the rectangular graph paper. This is the graph paper with which everyone is aware. Now here you can see that this horizontal axis, which represents certain negative numbers -10 to +10, and this horizontal axis will be used to represent resistance. Like I have redrawn the part of the graph only here for the sake of clarity. So horizontal line is nothing but this red line, which is used to represent a resistance which is ranging from 0 ohm to 13 ohm. And here in this graph paper you can see that the vertical axis is used to represent reactance from -10 ohm to +10 ohm. And since the reactance, it can be positive or negative depending on which kind of reactance we are considering. For inductive reactance, we'll be using positive y-axis, and for the capacitive reactance, we'll be using this negative y-axis. Since we are not much interested in the negative resistance, that's why the left side of this graph will not be used. Only we are going to use the first quadrant and this fourth quadrant. So here I have redrawn everything. You can see the positive y-axis, negative y-axis, and since we are not going to use the left part of this graph because we are not going to deal with the negative resistance, so nothing is shown here. Now these vertical lines, since I said that this horizontal line is used to represent resistance, here you can see it's a resistance. So all these vertical lines, they are representing fixed value of resistance and varying value of reactance. For example, if I consider this particular point, as long as I am standing on this horizontal line and at a value of 2, it means that I am talking about pure resistance. There is no reactance involved. But the moment if I talk about this vertical line which is passing through that 2, it means that the resistance is not changing. But since we are moving on this line, so something is changing. So that change is nothing but change in the reactance. For example, if I stand here, so it means that the resistance, even though it is 2, but the reactance is -9. If I move ahead upside, then the reactance reduces, and finally the moment I reach here on the horizontal line, the reactance becomes 0. If suppose I move further upward, then the reactance, it becomes positive and increases, and finally it will reach to 10. So here the impedance is 2 ohm plus j times of 10 ohm. It means that 2 plus j times of 10 ohm. So all these vertical lines, they are representing different values of resistance, and similarly all these horizontal lines, they are representing different values of reactances. Now we are going to see how this combination of horizontal line and vertical line can be used to represent different values of impedance. So for example, if suppose I have to represent a resistance of 10 ohm and a positive reactance of suppose 5 ohm. So since we are interested in the resistance of 10 ohm, so I will move this vertical line, I will place it at 10. Now this vertical line represents a resistance of 10 ohm, and since you can move along this line, so reactance is varying, but we are interested in a fixed value of reactance also, and that is nothing but 5 ohm. So I will take the help of this horizontal line, so I will fix it here. Now this horizontal line, it represents a reactance of fixed value, but since you can move from this end to this end, you can choose a different value of resistances, but the reactance is going to be fixed. Now the intersection of these two lines, it represents an impedance of 10 plus j times of 5. because this vertical line, as I said, that it represents a fixed value of resistance but a varying value of reactance. Similarly, this fixed horizontal line is representing a fixed value of positive reactance but a varying value of resistance. So the intersection of these two will represent a fixed value of impedance. Here it is 10 plus j times of 5. Now suppose you are interested to plot an impedance of 5 minus j5. Sorry, 5 is missing here, so I will take another example of 6 minus j times of 4, suppose. So this is 6 ohm resistance, you can see. Now reactance of minus 4 ohm. So now the intersection of these two line, vertical line which represents a fixed value of resistance and horizontal line which represents a fixed value of reactance, which is nothing but minus 4. So the impedance at this intersection point is 6 minus j4. Now you can note down that this vertical line and this horizontal line, they are always perpendicular to each other. So here you can say that the group of this vertical line which represents resistance and group of horizontal line which represents reactance, either negative or positive. Everywhere they are perpendicular to each other. It is just because there is a phase shift between the resistance and reactance of 90 degrees. Since the inductive reactance, it leads by 90 degrees with respect to the resistance, and this negative reactance, it lags by 90 degrees with respect to the resistance. This horizontal line and the vertical line must be perpendicular to each other. Now all this background will be used as it is in the understanding of Smith chart. So let's move to understand the Smith chart. Now this entire discussion will be used to understand how to plot impedance on the Smith chart and how to make use of the Smith chart to design high frequency circuit. So here we will begin with the resistance part. So in earlier graph paper we have seen that there were vertical lines which were representing different values of resistance. So here Smith chart is a circular chart, so there is nothing like straight line, but all the lines, they are modified into the circular lines or the curved lines. So here you can see that there are various circles, and every circle, it actually represents different value of resistance. For example, this horizontal red line, it represents different values of resistance like 0, then 0.3, 0.51, then 30, and finally infinite. So this outermost circle, which is the largest one, it represents a resistance of 0 ohm, and the second circle, which is little smaller than the earlier one, it represents a larger value of resistance, larger than 0 ohm. And here you can see that the smallest circle which appears in this figure, it represents a resistance of 30 ohm. Similarly, the largest value, which is nothing but infinite, the size of that circle is 0. That is, its radius is 0. That's why it is going to appear as a point and cannot be seen in this diagram. So here the conclusion is that all the horizontal circles, they are representing different values of resistance. The largest circle will represent 0 resistance, and a point circle which is going to be on the extreme right side, that will represent a resistance of infinite ohm. That is short circuit to open circuit. So short circuit is going to lie on the extreme left hand side, and the open circuit will lie on the extreme right hand side. You can see that all these resistance circles, they are going to share a common point on the right hand side, that is, they are tangent at this point, but on the left hand side they are separate from each other. So as long as you move on any of this circle, the resistance is not going to change. So if I move on the outermost circle, it means that the resistance will remain 0. But since you are moving, so something is varying. That variation from our earlier discussion can be variation in the reactance, but since we have not shown any reactance curved here, that's why we will not involve that part here. But remember that moving on any of this circle, it means that resistance is going to be fixed. Now how to read the resistance by horizontal line? Suppose you are moving on this circle, it means that as long as you are not leaving this circle and moving on this circle only, the resistance will remain 0.5 ohm. Similarly here. Now we'll move to the discussion of reactance. So already we have seen that the reactance, it is always perpendicular to the resistance. So we need to plot another kind of circles, and all those circles must be perpendicular to the earlier horizontal circles. So here you can see that this is that horizontal line on which the values of different resistance were mentioned in the earlier figure. Now since the reactance, either it leads resistance or it lacks resistance, it means that there is what 90-degree phase shift between the resistance and reactance. That's why this vertical line is drawn. This portion, it represents negative reactance, and this portion, it represents positive reactance. So here once again the circles are used, but this time these circles are going to represent different values of positive reactances. Like the smallest circle in this figure, it represents a reactance of 20 ohm, then this 10 ohm, then this smaller than that, and as the size increases, the reactance, it becomes smaller and smaller. So the minimum value of the reactance is going to be 0 ohm, for which the radius of the circle is infinite. And if suppose you are going to draw a circle whose radius is infinite and a very small portion of that curve is taken, it will appear as a straight line. So this horizontal red line is nothing but that portion of the curve which represents a reactance of 0 value. So actually you can see that this horizontal line is nothing but a reactance which is 0. But as the curvature increases, the size of or the value of reactance, it keeps on increasing, and all the circles, they are tangent at this point, and the upper side, they are open, means they are not touching each other. Similarly, the negative reactance is represented with the help of these lower circles. Now we are going to club these two circles which are representing different values of reactances, and the earlier circle which was used to represent different values of resistance. And since we have already seen that reactance and resistance, they must be perpendicular to each other because there is a 90-degree phase shift between them. Complete Smith chart will look like this. So this is the Smith chart. Now instead of having complete perpendicular circles which represents reactances, only part of the curve is used from that circle. The reason is what? Now already I have said that this outermost circle, this horizontal circle, it represents 0 resistance, and we are going to deal with the resistance whose value is 0 to infinite. So we are not interested in the negative resistance. That's why outside this circle there is a region of negative resistance. So here negative resistance is there, and since we are not going to deal with that, that's why these circles which are going to represent reactance, the remaining part of those circles are not taken into consideration. Only part of that circle is taken into consideration, so it becomes arc here. It's not a complete circle, but part of that circle, that is arcs, are used here to represent reactance, but the concept will remain as it is. Now everywhere the red circle and the black circle, they are going to be perpendicular to each other. It is just because these are the black circles, they are representing reactance, and the red circles, they are representing resistance. And since there is always a phase difference of 90 degree between them, that's why they must be perpendicular to each other always, and the concept will remain as it is. Like if suppose you are moving on this particular circle which represents a resistance of 0.3 ohm, so as long as you are moving on this circle, the resistance is not going to change. But you can see that when you are moving on this circle, you are coming across different arcs. Like here you are coming across arc whose value is plus J1. When you are reaching here, you are coming across this arc which is nothing but 0 reactance. When you are reaching here, you are coming across a new arc whose value is minus J1. Here it is minus 3 ohm. It means that as long as you are moving on this horizontal circle, the resistance is not going to change. But since you are moving, so something is varying. That variation is nothing but the variation in reactance. Same is true for the arc. As long as you move on any of this arc, the value of reactance is not going to change. It will remain fixed. Like if suppose I am moving on this arc, it means that I am moving on a reactance whose value is what? Plus J1. But since you are moving, you are coming across different circles, red circles. Here different red circle is there. So when you have moved from here and you have come to this point, it means that now the reactance is 1 but the resistance is 0.3. The moment you reach here, it means that the reactance is still plus J1 but the resistance is plus 1. When you reach here, the reactance is plus J1 only, but the resistance, it has got increased to 20 ohm. So you can see that the denser region, it contains larger value of reactance or the resistance. Now this graph is, of course this is a Smith chart only, but it is used to represent impedance. So there is another Smith chart which is used to represent admittance, and the difference, very little difference is there, and that difference is nothing but the rotation of the Smith chart by 180-degree angle. So you can say that that denser region now it has shifted on the left hand side. So still the concept will remain same. Here the circles, now since this is what admittance Smith chart, so circle, these red circles, it represents conductance. So the largest circle is going to represent zero conductance, and the smallest circle, which is going to be a point only, and it is somewhere here. Since it is a point, it's not appearing, but it is going to represent a conductance of infinite value. So you can see that the other circles, they are going to represent conductance larger than 0 but smaller than infinite. Same is true for these arcs. Now the upper arcs, they are representing inductive susceptance. That's why you can see that the values are negative, -10, -3, -1. So this represents inductive susceptance, and the lower arc here, it represents capacitive susceptance. So largest value, or you can say the larger the value, smaller will be the size of the circle or the size of the arc. Smaller the value, larger will be the size of the arc. So if you are going to represent a susceptance of 0 mho, then you need to work on a circle whose radius is infinite. So it is this circle actually, because we are drawing only the small part of that circle whose radius is infinite. It is going to appear as a straight line. So this horizontal straight line once again represents the reactive component. Here it is susceptance. Okay, and the concept once again same. As long as you are moving on a particular red circle, it means that the conductance will remain same, but the susceptance will keep varying. Similarly, if you move on any of this arc, then the susceptance will remain fixed, but since you are coming across different circles, it means that the conductance, it will keep varying. Now from these two Smith charts, you can conclude that the upper region is reserved or used to represent inductive behavior of the circuitry, either inductive reactance or inductive susceptance. So inductive susceptance, and here it is inductive reactance, and the lower portion, it is used to represent capacitive reactance, and in Y chart capacitive susceptance. So lower region is used to represent capacitive behavior, upper region inductive behavior, irrespective of the chart, which chart you are going to use.